problem, we're talking about radioactive decay known as alpha decay, in which we have an unstable nucleus and it emits a helium atom nucleus, which is called an alpha particle. An alpha particle is just contains 2 protons and 2 neutrons, so we know what the mass is, 2 of these guys plus 2 of these guys, 4 times the atomic mass unit, and it has a net charge of the 2 protons, because the neutrons are neutral, of course. So in this problem, we're going to assume we start with a uranium nucleus. So we start here with uranium, and then the uranium undergoes radioactive decay, undergoes alpha decay, and it transforms into a thorium. So it's going to be a little tiny bit smaller than the uranium. So there's thorium. And an alpha particle. That's going to be a lot smaller. It says that the alpha particle is initially at rest at the surface of the thorium nucleus, which is 15 femtometers in diameter. And a femtometer is 10 to the minus 15 meters. What is the speed of the alpha particle when it is detected in the laboratory? So when it's detected in the laboratory, it's gotten far away from the thorium nucleus, which we're assuming remains at rest. So this is how things look initially. And then finally, we have our thorium, which hasn't moved at all, and our alpha particle, which has gotten far away. So we're going to try and find the speed. We can apply conservation of energy here. When the alpha particle is at the surface of the thorium nucleus, those are two charges which are close to each other, going to have electric potential energy. In the final situation, the alpha particle has moved far apart. It has kinetic energy. This one is still and it doesn't have kinetic energy. It's far apart, so their interaction is pretty small, so there'd be no electric potential energy. So what we can set up with here is that E final equals E initial plus any work done by non-conservative forces. The non-conservative forces would be forces like friction. We don't have any of that in this problem, so the work done by non-conservative forces is 0, which means that the final mechanical energy is equal to the initial mechanical energy. So let's see if we can find out what the initial and final energies are, and then we can solve for the speed of the thorium nucleus, of the alpha particle. So this is going to be the initial situation. So our initial energy is equal to K initial plus our electric potential energy initial. Everything is at rest initially because nothing is moving at first, so our kinetic energy is initially 0. Plus our electric potential energy, which is K times Q1 times Q2 over R12. Got to be careful with R12 here. When we have 2 spherical charges separated like this, R is the distance between the 2 centers. So R, since the alpha particle is very small, the distance between the 2 centers is going to be about half the diameter. So R12 is about 1/2 the diameter of the thorium nucleus, or about the radius of the thorium nucleus. So 7.5 times 10 to the minus 15 meters. So let's fill in the charges that we know here. So we've got K. Our thorium nucleus has 90 protons. So the charge on the thorium nucleus is 90 times E. Our alpha particle has 2 electrons, so its charge is 2e. And we're dividing by the radius of the thorium nucleus, which is 1/2 the diameter. So if we want to simplify this, we've got 90 times 2 is 180. We've got a half in the denominator, so that half is going to come up top. So we'll get 360 times K times E squared over the diameter of the thorium nucleus. Okay, and again, if you wish, you could put your numbers in here and you could get a number for your initial energy to start with. Okay, let's also write down what our final energy is. So this is our final portion. And in the final part, they're far apart. So our final mechanical energy is the final kinetic energy plus the final potential energy. The final kinetic energy is the final kinetic energy of thorium that stays at rest. So our final kinetic energy then is the kinetic of thorium, which is 0, plus the kinetic of the alpha particle. So it's the mass of the alpha particle times the speed of the alpha particle squared, plus the final electric potential energy, which is K times Q1 over Q2 over R12, where R12 is the distance between the centers. R12 is big, so it's approximately infinity. It's really big compared to what it used to be. So this entire term is approximately 0. So let's simplify this just a little bit more because we know something about the mass of the alpha particle. So that's 1/2. The alpha particle has 4 protons, 4 neutrons, so its mass is 4 atomic mass units. So 1/2 times 4 gives us 2 times an atomic mass unit times V alpha squared. So let's put this in for EF, let's put this in for EI, and then we'll solve for our final speed. So E final is 2 times the atomic mass unit times V alpha squared equals E initial, which was 360 times K times E squared over the diameter of the thorium nucleus. Let's solve for V of the alpha particle. V alpha equals 360 times K times E squared over 2 times U times D of the thorium nucleus. Oh, and then we take the square root of both sides. So for the numbers we're going to plug in here, K is our Coulomb's constant, so that's 8.99 times 10 to the 9 newtons times meters squared over coulombs squared. E is our fundamental charge, 1.6 times 10 to the minus 19 coulombs. U is our atomic mass unit. On a test, that value might be given, otherwise you'd look that up in your book. 1.66 times 10 to the minus 27 kilograms. And then last, D, thorium, that was given in the picture there. D of the thorium nucleus is 15 times 10 to the minus 15 meters, because it was femtometers, which is times 10 to the minus 15. Put this through the calculator, we get 4.08 times 10 to the 7 meters per second. This is a pretty big speed, and in fact, this is probably approaching relativistic effects. And I think what that shows us is that there's a very strong repulsion between that alpha particle and the thorium nucleus.